So today I want to talk about functions. Functions are one of the core concepts in all of mathematics. They show up everywhere. They're incredibly useful and they can feel a little bit mysterious. So what I want to do is I want to talk about three metaphors or three ways of understanding what functions are and how they work. So the first first metaphor is to think of functions as actions. So think about the distinction between nouns versus verbs. And we can, roughly speaking, think of nouns as just like things, like objects, like the number 2, or triangle. And verbs are like the doing of things. So doing might be like squaring, or finding the area. So we've got just plain objects that sit around doing nothing, and then we have actions, right? So squaring is indeed a function that we might write like this. And just for a little bit of terminology, this is read as f of x equals x squared. So this f of x part is how you read this notation on the left. And the idea is that f is the function. So this f here is the function. And what it does is it's the action which does something to some object, like this x. Like, for example, f is the action that takes the object 2 and moves it, does something to it, which makes it into the object 4. And it takes the object 3 and makes it into the object 9. And you could imagine another type of function which takes an object like a geometric figure and makes it into the number which represents the area of that figure. That's a sort of less common, maybe more abstract idea of a function, but it's the same idea of this doing, when you take one thing and you make it into something else. You take 2 and you make it into 4. You take 4 and you make it into 16. So this is the first metaphor, functions as actions. Now, the second metaphor, these are all going to be related to each other, of course. The second metaphor is functions as machines. And this is something that you will sometimes see as a sort of like input-output box. You've got going in some number x, coming out some number x squared, and in the inside of the machine, maybe you imagine that you've got your x being split into 2 copies and then being multiplied together so that you get the output as x squared. So if you put 2 into this machine, then it spits out 4. If you put 3 into the machine, then it spits out 9, and so on. So this is very much like the action metaphor, except it gives you this sense that there's some kind of process in the background, which is taking an input, doing something to it, and creating an output. And indeed, many functions are specified like that. Like I might write down the function s of x equals x plus 1. And I can think of this as an action, but I can also think of it as just a mechanical procedure which adds 1 to whatever number you put in. Okay, so this picture, it's a kind of visual representation of an action, but the idea of the input-output nature of a function actually leads us to our third metaphor, which is functions as input-output lists. What do I mean? I mean, we can take this metaphor of the machine here and eliminate the machine and say, look, what's going on here is I have an association between 2 and 4. 2 an association between 3 and 9. 3 and 9. And maybe I have an association between many pairs of numbers. This is supposed to be 4. So this is maybe the most abstract representation of a function, but it's in some sense the closest to how mathematicians tend to think about functions, which is really just the machine in the middle is just a picture that you draw, but the real nature of the function at the end of the day is just this connection between the input and the output. It doesn't matter how you got from the input to the output. That's not actually something which the function can specify. We've seen, in fact, in another video, that this function that I wrote before, f of x equals x squared, could be viewed as what it looks like, which is take an input number, right? So take f of 2 and then multiply 2 times 2, and take f of 5 and then multiply 5 times 5. Or it could be viewed as take f of 5 and add up the first 5 odd numbers. 1 plus 3 plus 5 plus 7 plus 9. In another video I show that this idea of adding up the first n odd numbers always gives you the same number that you would get by squaring that first number you started with. The first 5 odd numbers add up to the square of 5. So if I have this machine here, then presumably the machine that multiplies 5 by itself and the machine that adds up the first 5 odd numbers are different machines. They're doing different things. But functions don't care about the how. They care about only the association between input and output, which is the same in either case. So that's why this third metaphor is closest to how functions are viewed in mathematical practice as simply associations between an input and an output. And in general, where you see functions are cases where there's something about the input which contains enough information to derive the output. So let me end with some examples of functions that illustrate this point. So one function you might have is b, the birthday function, which takes in a person and outputs that person's birthday. I don't care to specify an actual machine that somehow figures out the person's birthday. That's beside the point. The point is that this function has the job of taking in some piece of information, right? It's not a number in this case, but it's a person, and outputting something that you can derive from that input, which in this case is the person's birthday. Or you could make it their height, or the name of their father, or something like this. Another function might be the, let's call it the norm function, which takes in coordinates in the xy plane and outputs the distance to the origin, which in a picture would look like, you know, I have a point x, y in my plane. So the point is determined by these coordinates, x and y, the x coordinate and the y coordinate, and what I want to know is this distance. And of course, if you apply the Pythagorean theorem, this ends up being the square root of x squared plus y squared. So I have a numeric function here. It says take two numbers, x and y, square them both, add them together, and take their square root. And that just sounds like some random numeric function, but it also has a geometric interpretation which is predicated in the fact that if I take a point in the plane, that point encodes within itself the distance that it is from the origin, this point 0, 0. Just like a person encodes within itself that any of the details about that person, like the person's birthday. And just like a number, 1, 2, 3, 4, in some sense encodes within itself its own square, since I can get it squared just from the number. And I can get a person's birthday just from the person, and I can get the distance from a point in the plane to the origin just by knowing what that point is. So that's the idea of what functions are. They're ways of associating an input to an output, in which case the idea is that the input encodes some information and the function extracts that information.